class we were looking at the concept of what is known as convergence in measure. Right. So one thing that we observed is that if Fn converges to F almost everywhere, that immediately tells us that Fn converges to F in the measure. So when this triplet omega A mu is a finite measure space. Right. The converse need not be true. That's what we saw. And so if A mu is infinite, still the result may not hold. So, well, the result may not hold. We saw an example. Right. So then what is that is possible? Yes, so that's what we started with in the last class. Let omega A mu be a finite measure space if Fn converges to F in measure, then there exists a subsequence Fn k of Fn such that Fn k converges to F almost everywhere. Right. Proof. Yes. So we are already given that Fn converges to F in measure. Therefore, for every epsilon positive, there exists N naught in N such that measure of all those x in omega such that mod Fnx minus Fx bigger than or equal to epsilon, less than or equal to epsilon. So this is, well, whether you write bigger than or equal doesn't matter. For all n comma m greater than or equal to n naught, right? Or equivalently, measure of all those x in omega such that mod Fn plus m of x minus Fnx is bigger than or equal to epsilon. So the measure of this set should be less than or equal to epsilon for all n bigger than or equal to n naught and for all mn n. So in particular, for each, so we are now going to write it for epsilon equal to 1 upon 2 raised to the power k. For each k in n, there exists n which depends on this k in n such that measure of all those x in omega such that mod Fn plus m of x minus Fn of x bigger than or equal to epsilon, the measure of this set is bigger than or equal to 1 upon 2 raised to the power k. Less than or equal to 1 upon 2 raised to the power k for all n bigger than or equal to nk and for all m in n. Right. So we chose n1 as n of 1 and nk, sorry, as max of n of k comma n k minus 1. Just add 1 to that. Yes. For all k bigger than or equal to 2. Yes. So now consider the subsequence. Fn k. The claim is that this subsequence fn k, they converge almost everywhere. Yes. Yeah, the subsequence fn k converges almost everywhere. So it's enough to show that it's almost everywhere Cauchy, because we did not say where it converges. So we are only claiming that it converges almost everywhere. So in order to prove this claim, it is enough to show that fn k is Cauchy almost everywhere. Right. So for each k in n, let's consider the set AK, which is all those x in omega such that mod fn k plus 1 of x minus fn k of x is bigger than or equal to 1 upon 2 raised to the power k. Right. Then measure of AK is less than 1 upon 2 raised to the power k. This is first thing. Right. Now let me write Bn as union over k greater than or equal to n AK. So which implies that once you define this, then measure of Bn is less than or equal to summation over k greater than or equal to n measure of AK by countable subadditivity, and which is again less than 1 upon 2 raised to the power n minus 1. All these we saw yesterday. Right. So now we will have to show that this subsequence fn k is Cauchy. Right. So let epsilon greater than 0. Now choose k in n such that 1 upon 2 raised to the power k minus 1 is less than epsilon. Now for x in Bn complement, the complement, so we have chosen k, right? So Bk complement modulus of Fn k plus k prime of x minus Fn k of x. So now just add and subtract the next two terms. until you reach fn k plus k prime. So that you will notice that this is going to be less than or equal to summation I running from k to k plus k prime minus 1 modulus of fn I plus 1 of x minus fn I of x. Yes. And now this is only a finite term, so therefore this is less than or equal to summation over I bigger than or equal to k. I've made it infinite now. fn I plus 1 of x minus fn I of x, and each one it is in the complement, and therefore this is going to be less than 1 upon 2 raised to the power k minus 1, right, and which is less than epsilon for all k dash in here. Therefore modulus of fn k plus k dash of x minus fn k of x, if this is bigger than or equal to epsilon, implies, what does it tell us about x? If you choose x from bk complement, then modulus of fn of k plus k prime minus fn of k, that is going to be less than epsilon. So whenever this is greater than or equal to epsilon, what can you say about x?
At x, this series is divergent.
Louder.
At this x, this series f and k is not convergent.
No. See, my question is about x. What can you say about x? X, where does it belong to?
In Bn.
It belongs to bk. Therefore, so which implies that measure of this union over k dash, all those x and omega, such that modulus of fn k plus k dash of x minus fn k of x bigger than or equal to epsilon, this converges to 0 as k tends to infinity. So what does it tell us? What does it tell us? What can you say about the sequence f and k? So, well, wherever it doesn't converge, what is the measure of that set?
Arbitrary small.
You can make it arbitrary small because this goes to 0. What does that tell us? Or wherever this f and k plus k dash minus f and k, wherever it is greater than or equal to epsilon, what will happen to the measure of that set?
It will be less than epsilon.
You can make it as small as possible. Not only epsilon, even smaller than that.
Yes, sir.
Your right hand side doesn't depend on epsilon. It goes to 0 as k tends to infinity. That means that this sequence is Cauchy almost everywhere. Which means that the measure of this set is going to be 0. It's very small. Right? So that's what we wanted to show, in fact. So now let f tilde be the almost everywhere limit of f and k. Yes. So originally what is that is given to us? We are given that Fn converges to F in measure. Yes. So now claim is that F equal to F tilde almost everywhere. So only this much can be expected. So given that Fn converges to F in measure. So which immediately tells us that Fn k, this subsequence also converges to F in measure. Right. Now also, just now we saw Fn k converges to F almost everywhere, and so F tilde almost everywhere, and almost everywhere convergence implies convergence in measure. Fn k converges to F tilde in measure, and we know this, that if Fn converges to F in measure and Fn converges to G in measure, then F equal to G almost everywhere. So these two together implies that F equal to G, F equal to F tilde almost everywhere. That's it. And that's exactly what we want. All right. Yeah, so let me finish with an exercise. Let Fn be a sequence of R bar valued Borel measurable functions such that for every given epsilon positive, there exists a naught and n such that measure of all those x in omega with mod fnx minus fmx bigger than epsilon is less than epsilon for all n comma m bigger than or equal to m. Show that Fn converges in measure. Yeah, so basically this is Cauchy in measure, invariably. That's what it says. So, right. Fine. Now let's move on to integration. Yes. So one of the important topics and the main purpose of this series of lectures, let omega A mu be a measure space. Correct. So we are going to do it in stages. So first stage, stage 1, that means, so we are going to consider a simple function be a measurable simple function. Right. So once you know that it's a measurable, in fact, once you know that it's a simple function being measurable, I can write it in the canonical form. I equal to 1 to n alpha I characteristic function of E. So let be the canonical representation of f. So now let's define the integration. So the integral of f with respect to the measure mu. So let me denote it integral over omega f d mu is defined as integral over omega f d mu summation 1 to n alpha I measure of E. Yes. See, let's look at what we did in the case of Riemann integration. Let's see that you have a function from 0 to 1. This is 0, this is 1. So what is that we did? So basically we looked at the length of this straight line. Or so basically what did we do? So what does this mean? Integral 0 to 1. So let's say this is the constant 1 function f dx. So this is going to give us 1. So in some sense what we wanted is we wanted the integration to, whenever the function is Riemann integrable, we wanted such function to be also, they should coincide with what we defined here. That's our expectation. And therefore if you look at what have we done? What is this 1? This is nothing but the Lebesgue measure of the interval 0 to 1. So wherever there is a characteristic function, the natural thing that one would expect is the length of the interval, which is nothing but the Lebesgue measure, and that's exactly I have done here. In an abstract context, you have a function which is a linear combination of characteristic functions, and we expect the integral to be linear, and wherever there is the characteristic function, the integral that you expect is the measure of that set, and that's exactly I have done. Right. Now let's look at some easy examples. Yes, so first one, let omega equal to, let me choose it as AB, and the sigma algebra is the Borel sigma algebra, and the measure is the Lebesgue measure. So you consider the function f, which is the characteristic function of the set of irrationals in AB, right? So first thing that we wanted is we will have to write it in the canonical form. Yes, so let me write it in the canonical form. 1 times chi AB intersection with Q complement plus 0 times chi AB intersection with Q. Yes, so this is the canonical form because I have written it as characteristic functions of disjoint sets, right? Linear combinations of characteristic functions of disjoint sets, and their union is whole of omega, right? Now integral over AB f dm, this is what we wanted, which by our definition is 1 times measure of, or in fact m of AB intersection with Q complement plus 0 times measure of AB intersection with Q. Right. Okay, so what is measure of AB intersection with Q complement?
B minus A.
So 1 times B minus A plus 0 times, what is the other one?
0.
0. So which is nothing but B minus A. So maybe let me make a remark here that the above function cannot be integrated using the concepts of Riemann integration. Correct. So using the concepts of Riemann integration, you cannot integrate this function, but you can integrate this function using the so-called integration with respect to a measure. Well, this integration is what is known as Lebesgue integration. Let me even write it here. Lebesgue. So this whole thing is due to Lebesgue. He defined the whole thing for R with the Borel sigma and the, well, R with Lebesgue measurable sets and the Lebesgue measure, and it was Kolmogorov who extended to other. Right. Second one. Let's look at the same function as usual. So consider the triplet. Let me write it this way. Well, instead of AB, let me choose it as 0, 1. Doesn't matter. 0, 1, Borel sigma algebra. And then you consider the measure delta half. What is this delta half? Govind.
Yes, sir.
What is delta half?
Delta Dirac function at half.
So how do you define delta half at E equal to?
I don't remember actually.
Well, let me recall delta half at E. Yes, Kritika.
It is 1 if half belongs to E and 0 if it does not belongs to E.
1 if half belongs to E, 0 if half doesn't belong to E. Yes. Right, done. So this is what is the measure. Now you consider the same function 0, 1 intersection with Q complement. Right. Now, yes, start. Integral over omega f d delta half. Yes. Start. Which is going to be, well, so you need the same thing. Integral over omega 1 times characteristic function of 0, 1 intersection with Q complement plus 0 times characteristic function of 0, 1 intersection with Q. This function we are going to integrate with respect to the measure delta half. Right. So which by definition is 1 times delta half of 0, 1 intersection with Q complement plus 0 times delta half of 0, 1 intersection with Q. Yes, Govind.
Yes, sir.
Now tell me, what is delta half of first set? 0, 1 intersection Q complement.
0.
0, yes. Now for the second one, what is delta half of that?
1.
1. So which essentially is 0. Yes. If you change the measure, then the value of the integration changes. So if one changes the measure, then the value of the integral changes. Value of the integration. So whatever function that you are integrating, that changes, right?
Sir?
Ha.
Sir, we are studying general integration for any given measure space. But you written the topic as Lebesgue integration.
So this concept is what is known as Lebesgue integration.
Sir, first example or this whole concept?
This whole concept of integration initially was defined by Lebesgue, and therefore it is called as Lebesgue integration.
Oh, okay.
So let me make one more remark. That if E subset of omega and E is also measurable, then integral over E f d mu. Yeah, this makes sense because this d mu, what is this mu? This mu is the restricted measure. There's nothing but you can notice that this is the same as integral over omega f times chi E d mu. Yes. So they are one and the same. So if I write, in fact, so if I write f as summation alpha I chi ai, then this will imply that integral over E f d mu will be summation 1 to n alpha I. So this is when I, so this is the left hand side, and therefore this mu is nothing but the restricted measure, and therefore this is nothing but mu of ai intersection with E. That's what is the right. Now on the other hand, integral over omega f chi E d mu, which is integral over omega summation alpha I chi ai times chi E. Well, I have taken it inside d mu, but what is chi ai? Well, what is chi a times chi b?
Chi of ai intersection E.
Chi a chi b is chi a intersection B. In fact, this is also same as chi a plus chi b. Right. So which is equal to integral over omega summation alpha I chi ai intersection with E.
Sir. Sir, chi a plus chi b should be. I mean, how is it working?
Sorry. This should be chi a union b. Sorry. Thank you. Sorry. Yeah, thank you. No, this is not correct. Sorry. Right. Right. So this much you have. So now this I can write it as integral over omega summation over alpha I chi ai intersection with E plus 0 times chi E complement d mu. Because we have missed E complement here, and therefore this is going to be summation alpha I measure of ai intersection with E plus 0 times measure of E complement, but whatever be that, this is only 0, so therefore what is left is only this much. Fine. Yeah, and that's exactly what we wanted, right? So these two matches, right? So yes, so I don't have enough time to state the next lemma and then prove things. So I think it's time to stop here. So I need to prove monotonicity of the integral, linearity, and then how this integral gives rise to a measure. So all these things I'll prove it in the next class. So with this, let me stop here. If you have got any questions, please.